Hello everybody. Today we will solve one more problem on continuous beam with overhanging with the help of slope deflection method. Okay. So, here the problem is something like this. I will write down the problem. Okay. The problem has three supports. The first support is fixed in the nature, and the two more supports are simple in the nature, right. So, this entire beam carries a UDL, okay. The magnitude of the UDL is 50 kilonewtons per meter, 50 kilonewtons per meter, and this is also 50 kilonewtons per meter. So, let me name them. This is support A, this is support B, this is support C, and this is end. So, the portion CD, it is overhanging, that is if any beam it is extended beyond any support, so that portion we call it as a overhanging. So, here the portion CD it is extended beyond the support C, so that portion CD is overhanging, right. So, at this overhanging at the free end we have a concentrated load of magnitude 25 kilonewtons. Now, the span AB it is about 4 meter, the span is 4 meter, and its I value, that is moment of inertia, I is I, there is no change in the I value, whereas the span BC it is about 3 meter, and here I value is 1.5 times of the I, that is whatever the I value we have for span AB, it is almost 50% greater for the span BC. And the overhanging portion it is about 2 meter in span, and its I value is also I, there is no change in the I value. We have to analyze this continuous beam with the help of a slope deflection method, and we need to draw the shear force as well as the bending moment diagram. Okay. So, as usual I will start with the step number 1, that is finding the fixed end moments. See here solution. The step number 1, as usual it will remains determining the fixed end moments. Okay. So, in this step what we are doing, we are assuming the ends of the spans are fixed, and because of this fixed ends, due to the external loading on the beam, the end moments which are generating, so those are called as the fixed end moments. So, we need to determine how much is the fixed end moments. So, here the fixed end moments are MFAB and MFBA. So, this is end A, this is end B. So, this moment is MFAB and this is MFBA. So, here the span is 4 meter and I value is I, right. So, we need to determine how much is the fixed end moments at A and fixed end moment at B. For that we have the direct formula, MFAB is equals to minus WL square by 12 minus of here the W is 50 kilonewton into the span L is 4 meter. So, it is 4 square divided by 12. So, if you solve this MFAB, it yields to minus 66.67 kilonewton meter is the magnitude of the fixed end moment at A. Similarly, let me determine the fixed end moment at B because of this external load, that is MFBA. MFBA is equals to, because of the UDL, the formula is WL square by 12. Same formula, only the change in the sign. So, this will be 50 into 4 square divided by 12, which yields to MF BA equals to plus 66.67 kilonewton meter. So, these are the fixed end moments at A and B because of the fixed end conditions at A and B due to the external loading. Next, we have to repeat it for the span BC. So, for span BC also we need to assume both ends are fixed and we have to consider the loading as usual. The given loading we need to consider. The given loading is 50 kilonewtons per meter. 50 kilonewtons per meter. So, this is end B, this is end C. Because of these fixed end conditions, the end moments MF BC plus MF CB are developed. So, we need to determine the magnitude of these end moments. So, here MF BC, because of the UDL on the span BC, the formula will remain same, that is WL square by 12. So, minus of W is again 50 kilonewton, 50 into the span is different here. For the span AB it is 4 meter and for the span for BC it is 3 meter. So, here the span is 3 meters where I is 1.5 I. Okay. So, it is 3 square divided by 12. So, MF BC. So, if you solve this, you will get MF BC as minus 37.5, minus 37.5 kilonewton meter. Now, similarly, the other moment, that is MF CB is equals to, the formula to determine the fixed end moment is plus WL square by 12. So, it is plus into 50 into 3 square divided by 12, which yields to MF CB as plus 37.5 kilonewton meter. Now, here the portion CD, it is overhanging. So, because of this overhanging or because of this load, there will be a generation of final end moment, that is MCD. It is not the fixed end moment, it is the final end moment. So, we will directly get here final end moment MCD is equals to. So, if I consider the right side of the beam, so on the right side this 25 kilonewton is creating a clockwise moment, so it is negative. So, minus of 25 into its perpendicular distance is 2 meter. So, we will get MCD as 50 kilonewton meter as final moment. This we need to remember. Okay? For overhanging portion, it is not necessary to determine the fixed end moments, as because of the overhanging we will directly get the final end moments. And the moment at D, that is MDC, it is 0 because of the overhanging and a free end. So, the final end moment at D is always 0, right. So, here we have only 4 fixed end moments, right. So, now let us continue with the problem, that is the step number 2, it is writing the slope deflection equations. Okay. Step 2, slope deflection equations. Okay. So, for each span we need to write the slope deflection equations. These slope deflection equations are nothing but the equations to determine the final end moments. See here, As we are interested in determining the final end moments, we need these values, that is we need MAB, the equation to determine the MAB. We need an equation to determine the MBA. Similarly, we need an equation to determine MBC and MCD. We need the equations to determine these values. Okay. So, let us adopt the slope deflection method here. So, as per the slope deflection equation method, we need to write the slope deflection equations. So, MAB is the equation to determine the end moment at A. MAB is equals to, as per slope deflection equation, it is MFAB plus 2 EI by L into 2 theta A plus theta B minus 3 delta by L. So, here as per our calculations in the first step, the MFAB value is minus 66.67 plus 2 E. Here I value is I, so I will maintain the same thing, I by 4 into the theta A. Because of the fixed end support, the theta A value is 0 plus theta B, which we need to determine, minus there is no supports are sinking in the given problem, so the delta value will becomes 0. So, this yields to MAB is equals to minus 66.67 plus 0.5 EI theta B. So, let me call this as equation number 1. Similarly, we need to write one more equation to determine the MBA. Let us write MBA is equals to it is MFBA plus 2 EI by L into 2 theta B plus theta A minus 3 delta by L. This is the equation to determine the end moment at B. So, as per our calculations in the first step, the MFABA value is, it is plus 66.67 plus 2 EI by L, L here is 4 meter, into 2 theta B plus theta A is 0 minus delta value is also 0, which yields to MBA is equals to 66.67 plus EI theta B. Let us call this as equation number 2. So, these are the two slope deflection equations at A and B. Similarly, we need to write two more slope deflection equations for the span BC, that is to determine MBC and MCB. Now, MBC is equals to MFBC plus 2 EI by L into 2 theta B plus theta C minus 3 delta by L. So, as per our calculation, the value of MFBC is minus 37.5 plus 2E into I value. I value for this span BC is 1.5 I. So, I will consider that here 1.5 I. The span is 3 into 2 theta B plus theta C, both are unknown, the delta value is 0. Now, if you solve this, you will get MBC as minus 37.5 plus 2 EI theta B, minus 37.5 plus 2 EI theta B plus EI theta C. Let us call this as equation number 3. Similarly, we need to write one more equation at C, that is to determine the end moment MCB. So, MCB is equals to MFCB plus 2 EI by L into 2 theta C plus theta B minus 3 delta by L. So here MFCB is plus 37.5 plus 2E, I value is 1.5 I divided by span is 3 into 2 theta C plus theta B minus 0, that is the delta value is 0. So which yields to MCB is equals to 37.5 plus EI theta B plus 2 EI theta C. So let us call this as equation number 4. So these are the 4 equations to determine the end moments as per the slope deflection. Right. Next we need to write the equilibrium conditions so that we can determine the rotations at B and C. See, if I refer the equation 1, 2, 3 and 4, in all equations I can find EI theta B and EI theta C as the unknown variables. So these are nothing but the rotations at B and at rotation at C. To determine the rotation at B and rotation at C, what we need to do? We need to apply the equilibrium conditions at B and at C. So those are written in the step number 3, Shear. Step number 3, equilibrium conditions. So from the equation number 1 to equation number 4, what I can say, it is the unknown values which we need to determine, they are EI theta B and EI theta C. So theta B and theta C are the unknowns, so that we need to write the equilibrium conditions from B and from C joint. Okay. If I look into the support B, I have to take the algebraic, that is at joint B there are two members BA and BC. So for a equilibrium condition, the algebraic sum of moments at B, that is moments at B, must be equals to 0. That is the MBA plus MBC. When we add these two, the total moment or the net moment at joint B must be 0. So from equation number 2 and equation number 3, we will get the value of MBA and MBC. So as per equation number 2, the value of MBA is, it is 66.67 plus EI theta B. This is the value of MBA from equation number 2 plus the value of MBC. We can take it from the equation number 3, that is minus 37.5 plus 2 EI theta B plus EI theta C, right. This sum should be equals to 0. So here you can see we have one term of EIB here and two terms of the EI theta B in the next equation, next term. So totally it will be 3 EI theta B plus 1 times of EI theta C, which totally equals to, so 66.67 minus 37.5, which yields to the minus 29.17. If I take it on the other side, it will be, sorry, plus 190 plus 29.17. If I take it on the other side, it will be minus 29.17. So let us call this as equation number 5. Similarly, I need to write one more equation at C, that is at joint C, algebraic sum of moments at joint C must be equals to 0. If I see the joint C, at joint C there are two moments, one is MCB, another one is MCD. So that is MCB plus MCD equals to 0. The value of MCB we will get from the equation number 4, that is 37.5 plus EI theta B plus 2 times of EI theta C. This is the value of MCB. Whereas the value of MCD which we have calculated in the step number 1 as minus 50 kilonewton meter. So this is 37.5 plus EI theta B plus 2 EI theta C plus minus of 50 kilonewton, right. So when we solve this, we will come out with one more equation as EI theta B plus 2 times of EI theta C. This is equals to minus of 12.5. So if I take it on the other side, it will becomes plus 12.5. So let us call this as equation number 6. Now we have two simultaneous equations, that is equation number 5 and equation number 6. In both the equations we have EI theta B and EI theta C as the variables. If you solve these two equations simultaneously, we will get the value of EI theta B and theta C. That is solving equation 5 and 6, we get the value of EI theta B and EI theta C. EI theta B, it is about minus 14.68 radians, and the EI theta C is 13.33. Sorry, this is 14.1, is 13.334 radians. So these are the rotations at joint B and joint C. So once we have these rotations and the slope deflection equation, so we can easily determine the final end moments. That is step number 4. As per the step number 4, we can calculate the final end moments using the slope deflection equations. Okay. Shear. So we have the equation for MAB. Equation for MAB is minus 66.67 plus 0.5 EI theta B. So the value of EI theta B we have calculated it as 14.168. So I will substitute that value as 14.168, which gives me minus 73.75 kilonewton meter. So this is the final end moment at B. Similarly, we need to use the slope deflection equations and calculate the value of MBA, BC, CB and CD by substituting the value of EI theta B and EI theta C respectively. So which yields me around like this. The MBA, the final end moment at B, it is 52.50. It is 52.50 kilonewton meter. MCB, it is minus 52.50 kilonewton meter. MCD, it is 50 kilonewton meter. MBA, maybe MBC, MBC. This is MBC, this is MCB. The MCD is minus 50 kilonewton meter, and the MDC, because of the free end, it is 0. So these are the final end moments. Next, our duty is to represent these end moments into the given loading diagram. So see here, the value of MAB, it is minus 73.75 kilonewton. Minus indicates it is anticlockwise in the direction. So here I need to represent this as anti-clockwise. So it is 73.75. So this value will be, it is 73.75 kilonewton meter. Similarly, the value for MBA and MBC as per our calculation, it is MBA is plus 52.50, plus indicates it is clockwise in the direction. So we have marked it as clockwise, correct. MBC it is minus 52.50, minus means it is anti-clockwise in the direction. So these both together it is 52.50 kilonewton. So one is anti-clockwise, another one is clockwise. So similarly, the moment at C, that is MCB and MCD. MCB is plus 50 kilonewton meter and MCD is minus 50 kilonewton. So plus indicates clockwise and minus indicates anti-clockwise, which is as I have represented in the diagram. The magnitude is, it is 50 kilonewton meter, right. So once we represent these things, so we can use these end moments to calculate the final, we can use these end moments to calculate the support reactions and also the maximum bending moment at the beam. See, step number 5, support reactions and maximum bending moments we can calculate. To do this, we need to consider each span separately. So let me draw the free body diagram of each span separately. Okay. So let us say this is the span AB, which is about 4 meter, right, and which carries a UDL of magnitude 50 kilonewtons per meter. So because of this loading system, we know there the end moments, end moment at A and end moment at B. The end moment at A is 73.75 kilonewton meter and the end moment at B it is 52.50 kilonewton meter. So this is end A, this is end B. So let us consider this support reaction as RAB and this support reaction as RBA. So we need to determine the value of RAB and RBA and also how much is the maximum positive bending moment in the span AB. So to do that, what I need to do here is I need to impose the equilibrium conditions on this free body diagram. So if I impose the moment condition about A, that is algebraic sum of moments due to all the forces about point A must be equals to 0. So here you can see, if I take moment of all the forces about A, this RAB doesn't create any moment because it is passing through the point A, leaving no perpendicular distance. Whereas this 50 kilonewton UDL creates a clockwise moment about A point, and this reaction RBA creates an anti-clockwise moment about A point. Apart from these two loads, we have one anti-clockwise moment and another one is clockwise moment. All these things we need to consider into the calculation. So let us consider all these one by one. So first, this 50 kilonewton creates a clockwise moment. So 50 into its span is 4 meter. The concentration of this UDL acts at the center, that is 4 by 2 minus this reaction creates an anti-clockwise moment. So it is minus RBA into its perpendicular distance with respect to A, it is 4 meter. Then we have one anti-clockwise moment, so it is minus 73.75, then we have one clockwise moment, that is 52.50 equals to 0. From this we will get the value of RBA as, if you resolve this equation and determine the value of RBA, you will get RBA as 94.69 kilonewton. So it is a positive value, it means its direction is vertically upwards. Next, we have got one support reaction. The second thing is we need to determine the another support reaction, that is RAB. To determine the RAB, let me impose the another equilibrium condition, that is algebraic sum of all vertical forces must be equals to 0. So here in this condition, what we need to do here is we need to consider all the vertical forces which are acting on the span AB. If you look into the diagram, you can see that this 50 kilonewton is acting vertically downwards, whereas this RAB and RBA, these two support reactions are acting vertically upwards. So let us consider upward forces as positive and downward as a negative. Then equation will be something like this: RAB plus RBA minus 50 into 4 equals to 0. So in this equation we have two unknowns, RAB and RBA. The RBA value which we have already determined. Substitute this RBA value into the equation, you will get RAB very easily. So after substituting the RBA value, you will get RAB value as 105.31 kilonewton. So this is also a positive value. It means its direction is vertically upwards, right? So here what we have done is we have calculated the support reactions. Now we need to calculate the maximum bending moment. To draw the SFD, we need that value. To calculate maximum bending moment, what we need to do here is we need to draw the shear force diagram. Okay. So with the help of the shear force diagram, we can locate the position of the maximum bending moment so that we can easily determine. So in the previous classes we have discussed how to draw the shear force diagrams. So let me start with the point A. At point A we have a reacting force RAB, which is positive, that is it's moving vertically upwards. Its magnitude is 105.31 kilonewtons. After point A till B point we have a vertically downward UDL. So it is 105.31 minus this UDL, that is 50 into 4. So which yields about minus 94.69 kilonewton. So this is a negative value. Negative value means I have to take the shear force diagram to the negative side. So this is 94. It is 94.69. But at a B point we have another reaction, that is RBA, which is plus 94.69. So this minus 94.69 plus 94.69, which is equals to, the sum is 0. So I have to take this diagram to the upwards till 0. So this is a positive shear force and this is negative shear force. You can see here this shear force variation, it is crossing the datum line at some point. So this is a point where we can see the shear force is 0. And we all know that wherever is the shear force is 0 or the minimum, at that particular point we can expect the maximum bending moment. So we need to determine the location of this point. If I consider this distance as x, let us say ABC E point. So this is, it is 4 minus x. Okay. So by imposing the similar triangle concept, we can easily determine the value of x. So it is x, the base of this triangle, to the height, that is 105.31 0.31. This ratio must be equals to the other triangle, that is base of this triangle 4 minus x divided by height of the triangle, that is 94.69. If you cross multiply and calculate, you will get the x value as 2.106 meters. That is the distance at which we can find the shear force is 0. It means exactly at this location we can expect the maximum bending moment. If I call this point as E, let me calculate the bending moment at E by considering the left portion. So if I consider the left portion with respect to this point E, on the left side we have 1, 2, 3, three forces which I need to consider into the calculation. RBA with respect to E, it is creating a clockwise moment, so left side clockwise is positive. RAB it is a positive value 105.31 into its perpendicular distance. So this value, as we have calculated, it is 2.106, right. So if I consider that, so it is 2.106 into, sorry, not into, the UDL on this portion, it is creating an anticlockwise moment. So it is minus 50 into 2.106 into 2.106 by 2, right. And apart from these two, we have an anticlockwise moment. So it is minus 73.75. So this gives me the bending moment at E, which is, we can say it is a maximum positive bending moment. It is about 37.15 37.151 kilonewton meter, right. So with the help of these values, we can draw the shear force and bending moment diagram. See here. So these are the projection lines which help us to draw the shear force and bending moment diagram. So let me say this is a shear force diagram and this is bending moment diagram. The shear force diagram is exactly the same thing as we have drawn. Okay. It's a positive, it's a negative shear force, 105.31 kilonewton, and this is about 94.69 kilonewton. If you want to draw the bending moment diagram, so you need to consider each span separately. For span AB, the A is on the left end and B is on the right end. So left side we have an anticlockwise moment. So left side anticlockwise, it is always a negative moment. So let me consider a point below the line which indicates a negative moment of 73.75 kilonewton meter. On the right side we have a clockwise moment. So right side clockwise is also a negative moment. So let me consider that is also somewhere here. It is 52.50 kilonewton meter. Now somewhere here at a zero shear force, that is at point E, we found that the bending moment is maximum and it is positive. So that is, as per our calculation, it is 37.151. So let me consider that here, 37.151 kilonewton meter. Because of the UDL, the variation in the bending moment diagram will be parabolic in the nature, right. So this is the bending moment diagram for the span AB. Similarly, we need to do the same calculations for the span BC and continue with the shear force and bending moment diagram. Okay, see it. Now let me draw the free body diagram of the span BC. On span BC we have a UDL again, right, which is of 50 kilonewtons per meter. Apart from this UDL we have two bending moment. So one is MBC, it is about 52.50 kilonewton meter, and MCB it is 50 kilonewton meter, right. The span is 3 meter. Span is 3 meter. So let us call this support reaction as RBC and this as RCB. Okay. So we need to determine the support reactions RBC and RCB, and also we need to determine how much is the maximum positive bending moment about the span BC. So to do that, let me impose the moment condition about B and equate it to 0. So if I impose moment condition about B, then this 50 kilonewton creates a clockwise moment. So 50 into 3 into 3 by 2. This RCB creates an anti-clockwise moment, so it is minus RCB into perpendicular distance is 3. Apart from these two forces, we have one anti-clockwise moment, another one is clockwise moment. So anti-clockwise moment minus, it is 52.50, then clockwise moment it is plus 50 equals to 0. So if you calculate the value of RCB, it is yielding about the 74.16 kilonewtons. It is a positive value, it means its direction is vertically upwards. Now I need to impose the another equilibrium condition, that is f of y is equals to 0. So here these two reactions are acting vertically upwards. Let us consider them as positive, RBC and RCB. This UDL is acting vertically downwards, so let us consider it as negative. So here we have two unknowns, RBC and RCB. RCB value we have already calculated. Substitute the value of RBC here, you will get RBC as 75.23 kilonewtons. So now we need to calculate the maximum bending moment. To calculate the maximum bending moment, first we need to decide the position where the maximum bending moment will occur, right. So it is exactly similar to the previous span what we have done, because there also we have the UDL and here also it is UDL. You can draw very easily 75.23 kilonewtons, positive bending shear force, negative shear force. This is about 74.16 kilonewton. So somewhere here we can say it is the point where we have the zero shear force. So at this location we can expect the maximum bending moment. So let me call this as x1. So this distance is 3 minus x1. Okay. So let us say somewhere here we have the position. So I need to determine the position of x1 now. So to determine this x1, I will impose the similar triangle concept. So it is x1 by 75.23. This ratio must be equals to the 3 minus x1 divided by 74.16. If you cross multiply and calculate, you will get the value of x1 as 1.52. It is 1.52 meter. So you can say that at a distance of 1.52 meters from the B point, the shear force value is 0. Exactly at this location, the bending moment will be maximum. So we need to calculate the bending moment at this location. So let us say MF. To calculate MF, again I will consider the left portion with respect to this point, right. So on the left side we have one reacting force RBC, which is creating clockwise moment. So left side clockwise is positive. RBC value is, it is 75.23 into this distance, it is 1.52 minus the UDL on this portion, it is creating an anticlockwise moment. So left side anticlockwise is negative. So it is 50 into 1.52 into 1.52 minus we have this anticlockwise moment. So it is minus 52.50. So if you calculate this, you will get the MF. You will get MF as just 5 kilonewton. It is just 5 kilonewton a meter, right. So with the help of these values, again we need to draw the shear force and bending moment diagrams. So this is the same diagram which I have drawn here. So let me repeat it. Sorry. So this is about 75.23 kilonewton. This is something about 74.16 kilonewton, right. It is a positive shear force, it is a negative shear force. Now when it comes to the BC, so let me consider B is on the left side and C is on the right side. So left side we have an anticlockwise moment, so left side anticlockwise is negative. So consider a point below the line. Right side we have a clockwise moment, so right side clockwise is again negative. So consider another point below the line, which is about 50 kilonewton meter. Okay. So somewhere here, so we have the zero shear force. It means at this location the bending moment will be maximum. So as per our calculation, we have got it as just 5 kilonewton per meter. So let me consider that here. It is just 5 kilonewton meter. Sorry, somewhere here. It is 5 kilonewton meter. So because of the UDL, variation in the bending moment diagram is again parabolic. So let me draw an parabola, right. So after this we have only this overhanging portion that we can do it separately. The overhanging portion is very easy, we can do it very easily, right. See here. So let me consider this CD portion. So here we have only one reaction, so R CD, that's all. At D we don't have any support, so we don't, it's not necessary to consider any support here. This is about 25 kilonewton. Apart from this, we have a moment, that is MCD is equals to, that is 50 kilonewton meter. As this distance is, it is about 2 meter. So, we have already found the value of final end moment MCD and MDC is 0. So, what we need to do here is we need to just determine the value of RCD. To determine the RCD, what I need, I can impose the vertical condition directly. So, there are two forces which are acting vertically, one is vertically upward and another one is vertically downward. So, this RCD is acting vertically upwards minus this is acting vertically downwards equals to 0. So, the RCD value is 25, it is 25 kilonewton. So, with the help of this we can draw the shear force diagram. You can see RCD is 25. So, it is a plus 25, I need to take it vertically upwards. So, after this till D point we do not have any loading on the member. So, let me maintain the constant shear force diagram. So, at C point we will again meet with, sorry, at D point we will meet with this 25 kilonewton which is vertically downwards. So, it is plus 25 minus 25 0. So, this portion is, it is a positive shear force, right. And if I consider this for bending moment, so C will be on the left side and D is on the right side. So, left side we have an anticlockwise moment, it means it is a negative which I have marked as. Right side MDC, it is a 0. So, this is a point. Because of the point load, the variation in the bending moment diagram is linear, right. So, as this is the datum line, whatever the diagram which is there above the line, it is a positive bending moment and below the line it is a negative bending moment. So, let us mark it. So, it is a negative, positive, negative, positive, negative. So, hatch this so that we can make it little beautiful. Right. So, this is how we need to analyze the beam with overhanging and how we need to draw the shear force and bending moment diagrams, right. Okay. Thank you.